Okay, so in the last section, we took a look at designing good sample surveys, and in this section, we're going to take a look at designing experiments. All right, so in the end, we're going to end up putting these two together, our simple random sampling and our experiments. Just keep in mind as you're going through this section that the wording and vocabulary in this section is specific to experiments versus the wording in the last section. All right, so what are you going to be able to do in this section? Understand the difference between observational studies and experiments, understand the language of experiments, which is going to be very important, apply the three design comparative experiments. Remember, that's one of the two experiments. All right, so let's just take a look at the difference between an observational study and an experiment. Really, the only major difference between an observational study and an experiment is that an observational study looks at an individual and measures something. We use it to describe groups, compare groups, or look at a relationship between variables. Observational study is you sitting on the side of the street observing how many red cars come by. You walking into a classroom and observing how many people have red hair, brown hair, black hair. Walking into a track practice and observing how many people are standing around versus how many people are doing the workout. An experiment deliberately imposes some sort of treatment on an individual to measure their response. So the difference would be going into the classroom and giving half the people Coke and half the people caffeine-free Coke, and then seeing if the students had more energy throughout the class period. It would be going to a parking lot and putting one type of gas in one car and the other type of gas in the other cars, and checking to see if one car gets better gas mileage than the other. Okay, so it's actually imposing a treatment on our experimental units. When our goal is to understand cause and effect, experiments are the only way to have convincing data. All right, observational studies don't impose any treatment, so we cannot observe cause and effect from an observational study. So the distinction between an observational study and experiment is one of the most important distinctions. So when you read a scenario, make sure you understand the difference between an observational study versus an experiment, okay? And just make sure that you understand the only way to observe cause and effect is through an experiment, a well-designed, randomized experiment. Right, so this is Okay, so just take a minute and read this article about the coffee buzz, all right? And then I want you to answer the question, is it observational or experimental, and think about why. So go ahead, take a second and read it. If you need to, pause it, and then we'll go on to the next slide to take a look at the answer. Okay, so what'd you guys decide? This, hopefully you were correct, is actually an observational study, right? It's an observational study because we can't be sure that drinking coffee is the cause of longer life. It could be something else associated with drinking coffee that's the cause that we'll talk about in a few slides, talk about later in a few slides. So what is the reason that coffee drinkers live longer? Was it the coffee, or did they exercise more? And we were just physically looking at a group of people, looking at whether or not they drank coffee. Okay, we weren't imposing coffee or no coffee. They were already either drinking it or not drinking it, and then looking at the results. So the Pew Research Center is famous for its observational studies. So if you ever want to take a look at some of the observational studies, they're actually very interesting. Go to the website below and take a look. So they have excellent sampling methods, and then they ask them questions based on the data that they're looking for, but it's all sort of after the fact. Okay, so it's all observation. Okay, so here's just a few examples for you to try. Please click or copy and paste those links into your website. Take a look, and I want you to decide for the first question, after reading the article, I want you to decide whether or not it was an observational study or a designed experiment. For this second one, read carefully and listed was it study from and then they also results. Okay, so the first one was a little bit of a tricky one. It was actually an observational study. The key is that the researchers didn't force the veterans to have PTSD. They observed parts of the demonstration with PTSD or didn't have it. Okay, one thing to the last one, but one piece, they 15 days, and then compare the 17 people are had, and then they had 4 people active and take and see them, they look at their health. Okay, so just take a minute and read this. We're going to be taking a look at this specific scenario throughout this section. Okay, take a minute. If you have any questions on it, please let me know. But we're going to look at some of the key aspects of this experiment. So like I said, take a minute and read the scenario. Okay, so this is actually an interesting study, so just a quick summary. In the first example, they were either women already took the hormone replacement or they did not take the hormone replacement, and then they took a look at the risk of a heart attack based on whether or not the women had taken it or not taken it. Now keep in mind, in this situation, it's an observational study because they took a look at whether or not they had a heart attack after the women had already decided whether or not they were taking hormone replacements, and they chose whether or not to take them. So that was an observational study. Okay, they did not impose any treatment. However, they decided to conduct an experiment. Okay, experiments didn't let the women decide whether or not they were going to take them. So basically, they were randomly assigned whether they would get a hormone replacement pill or a placebo pill. We'll come back to that word later. All right, and then the assignment is done by coin toss. So they were randomly assigned whether or not they got the placebo or the hormone pill, so that all women were equally likely whether to get the treatment or to not get the treatment. All right, so let's just take a few minutes and look at the key aspects of this experiment. So if you take a look, though, obviously the experiment had much more information about cause and effect than the observational study. Okay, so what was important for that experiment? Number one is what can we do to studies of that one family because one of girls. So to know whether it's probably whether giving the pill or actually advising the exercise looking very something that possibly could cause hazards, but actually not part of it. So it can come from knowing there's games measurable and no variable not the response, but may influence on. X could use when two variables are associated, so therefore the result will be similar. Taking as a new couple and all of them and something that affects the group and so we can sleeping and can find if you love a division of one variable for sleeping or the actual new curriculum. So the goals of one are also for the lawyer is a variable would have the other types but that effort. Okay. So if you're asked to number one, make sure you explain how variable is associated with variable. So the variable is a variable statement. This variable shows the variable that responsible. Here's an example. When you call health, it will more or health for example. We just did exercise in the explain how to associate with another. It can more not exercise. That person would decide more. They have it. This exercise when have less heart attacks. So if you as to find the variable, if you actually variable, if you cannot know between a variable or how it's is related is related. Okay, let's just say that part. You can make okay, no, this is not something that I just stated people taking calls. You want to take examples like this. All right, let's say diet and hormone pills. So the hormone pills are more likely to take out health and fight. That's how they're and they'll and perform what they are. Since they have health and relationships. So it's take out quick funny be influence groups. Here's your normal and see, okay, well, health and growth. All right, so the language of experiments. So we talked about the language in the last episode. Let's talk about the language. So committed study including the improvement on both sides. Okay, so the objects are called arcness into a response product. So because number one, this applied rule is called a treatment. Okay, separate variables, the treatment information is on the variables. You have one treatment. Several separate variables includes variables to the treatment are clear who you to. Well, you have to how the explain variables in the medical first. Maybe especially so we make not see a hormone pill, a hormone pill, and diet. So for those hormones and diet. So each treatment is what happens to how we offer. Okay, so 50 grams a 100 grams of hormone will be left in the factors and will benefit. All right, if there's only one set of treatment factors and we'll say treatment, so if was just a hormone pill factor, then there's only one hormone pill and it's the same as treatment of the hormone pill. So the lower, there's more than variable. So look at the rules of the factors. Okay, so you might hormone pill knows it. There's some size for the rules even complete for all and separate little factors. This function we have exercise or take the booster. Pills are exercise outside, hormone pill, factors, hormone will be for rules. Exercise hormone pill, exercise no hormone pill, no exercise hormone, no exercise hormone pill. The problem is. So this what we do is I the chance will then we with your comments the factor level. So you might actually enter factor level and decide. So you take this and then decide. Okay, so if I did able to find all right, so number one, the experimental units were the tomato plants. They're not surprising. The two variables are the same factor. One was size and water, so it's like big and big foods. The response variable boys, the tomato foods, that's for air and water, so the factor name is and then little combinations of things. Okay, now the treat services are a combination that can be used for all first. So the level 7. So all the first fertilizer, have to get water, fertilizer 1 color, and the other that's only 1 color. All right, so I don't know if any of you have heard of the TED Talk, but if you would just take a minute and watch the short TED Talk video on how to buy happiness, he describes a neat multi-factor experiment to determine if money can buy happiness. After this the video, figure out how many factors are simple. Don't use instruments. You first the money and allows the options. Remember your factors are big, and how you break down. It's the rules and actually all right, so go ahead, read this situation. Hopefully, you have to it. My whole team read it and see my experiments, memory, and circles, and what factor like the factor loves, and okay, so I'm going to experimental units correctly. Okay, so the tricky part was the experimental units were the 376 households, not the 812 people. The treatments were not assigned to individual Okay, so experiments are often the preferred method for examining the effect of one variable on another. I'm saying treatment and influence and that whole experience has the power to determine we could nine if you don't have the going to determine how that. Just look at example. Okay, if you're 12 offer, the online of those for 20. They line group 17. That is a long time class where you know the online was more effective. Just look at this in this case would also be put in treatment that's happening. I need to see an experiment to the question. Okay. So for this experiment, a group of subjects, the students, so what we're is what's in addition to the college so we say okay, so how do we experiment badly? So just about how we talked about how they were talking badly. The main part of the design in the INT course example. Okay, we're going to treatment and response. So in the lab, there's no how to experiment people deal a lot of your conditions. Also, as I said, you have to okay, just have take and look at ACR and compare it. Okay. So how many more things we control down the character? So you means to go first the monument and similar things to go. Control is you have to have treatments. Or isn't if treatments that they're great place. So you make sure that that's the filter. So then plus bias right. So this question they buy so I will choose the course and I will on it that will use bias. And if you're missed, assignment means how do you and choose the assignment or a answer. Okay, so how exactly does random assignment help reduce bias? Sure, example isn't a bias. I ran with an entry entity. Let's go through random and take out versus non-short one about the groups. Also, get experimental to roughly equivalent in C tutorials who want both are with and went off in the groups and so that's the fact that there's we just recommend the all right, so let's just take a look at this. We're gonna asked the question, does caffeine affect pulse rate? Ooh. So many people consume caffeine. It seems to caffeine. So that's usually here's the pulse. So caffeine next again after 10 minutes increase in pulse rate. So those people speak 2 seconds in your caffeine agreement. It shows a symbol. When you okay, so let's see how this was done. So how could we use random assignment in order to see if caffeine affects pulse rate? So number one, identical pieces of paper. This is sort of like the hat method. All right, use 30 identical pieces of paper. Write A on 15 and B on the other 15. Mix them thoroughly and have each student select one. Then ask each student who received an A to drink the cola and each student who received a B to drink the cola without caffeine. All right, so that we're randomly assigning. We're not taking a simple random sample, we're randomly assigning. How could we do that using technology? These students will be able to pick control outcome. And the way to do it table. So it's from okay, so how do I create a completely randomized design? So in a completely randomized design, the treatments are assigned to the experimental units by chance alone. So whether or not we get caffeine or don't get caffeine is assigned to the units completely by chance alone. Some experiments may include a control group. What's the control group? That's a group okay, so what is it like? You go to with those first. You randomly assign them. You're going to group I'm going to do. If you students being no kind of free for the so I show you and how you so there's so out for to include group assignment of group not caffeine, and then we are measuring a B set. Okay. So randomized comparative experiments, so we're comparing caffeine versus no caffeine, are designed to give good evidence that treatments actually cause different results. So the 3 principles are design. Well, as the variable comes with value will occur, we'll know whether it's natural or they will be hair sign differences in the random assignment is imperative. Hey, it uses chance and pyramid limits. This rate with group experiment as well as the local articles. So just like an equation not being over and over again in statistics, they do not units true. Like if this treatment distinguishes the change of more than enough units in group. Okay, why is comparison important? Comparison is important because when we're designing an experiment, we have to take a result out. And those getting felt through. Random assignment must be a link section that is most to be a problem. You make some pre both teachers tend to shape it that less money of us don't know there's a could be on the link is friend know if it's or word conversation line. Watch it again for next over. This means there's more more to be for us. Completion of the working thing across is other things that okay, so let's just take a minute and look at a well-designed experiment. If you could just take a second and read this particular well-designed experiment investigating aspirin and heart attacks. We will be looking at some of the vocabulary in this section and describing how this well-designed experiment meets the 4 principles of experimental design. So go ahead, pause the recording if you need to, read it, and then we'll take a look at it. Okay, so just a couple things I wanted to point out is the fact that the subjects in the experiment were 21,996 male physicians. There were 2 factors, not 4. Okay, the 2 factors were the aspirin and the beta-carotene, and then there were 2 levels within each of those factors. So that meant that there were a total of 4 treatments. Okay, and we'll take a look at those treatments on the next slide. And then 1/4 of the subjects were assigned at random to each of the following treatments. Okay, so I just wanted you to take a look at some of the vocabulary in the second section. All right, so some of them were given aspirin, some of them were given something called a placebo, and we're going to take a look and see what a placebo is in a minute. Okay, and then on with the beta-carotene, they also took beta-carotene or placebo. So let's just take a look on the next slide and see what that placebo actually does for our experiment. And as they did this experiment, they found out that the difference is large enough to give evidence that taking aspirin does reduce heart attacks. They found out that beta-carotene did not have any effect on preventing cancer. Okay, so in this experiment, they decided that they were able to establish cause and effect. So here was just the experiment. 4 levels, which were the 4 treatments of our experiment. So one-fourth of the participants took aspirin and beta-carotene. 1/4 of the participants took aspirin and a placebo. 1/4 took a placebo and no aspirin and took the beta-carotene, and then 1/4 basically got no drug. They did not get the aspirin, which was the placebo, and they did not get the beta-carotene. Okay, so you saw the word placebo in the previous slide. What exactly is a placebo? So a placebo is a dummy pill or an inactive treatment that's indistinguishable from the real treatment. The placebo for aspirin and aspirin look and taste exactly the same, so the person that's in the experiment doesn't know whether or not they're actually getting the aspirin or the placebo drug. Now we're going to see, what does this placebo drug do for our experiment? How does it contribute to the 4 principles of experimental design? All right, so using that problem that we just looked at, we're going to explain how each of the 3 principles of experimental design was used in the physician's health study. Number 1, comparison. So here's where the placebo comes in. The researchers used a design that compared both of the active treatments to a placebo. So we compared the beta-carotene and the aspirin to a placebo or dummy drug. So that basically gives us a comparison so that we can help to establish cause and effect. All right, there was random assignment. The random assignment was used to determine which subject received each of the 4 treatment conditions. This helped ensure that the treatment groups were roughly equivalent to begin with, so this helped reduce variability within my treatment groups. Okay, control. So the experiments used subjects of the same gender and occupation. All the subjects followed the same schedule of pill taking. All right, so remember, you want to try to control for some of those lurking variables. So maybe if gender, female, male and female, we wouldn't know if it was the drug or gender. Okay, we controlled for that by choosing all males. Occupation, so they're all male physicians. So that's going to maybe help control the fact that male physicians are going to take better care of themselves because they're interested in a healthy lifestyle. And replication. So replication, remember, doesn't mean doing the experiment over and over again. It just means that there were enough participants in order to make it valid. Okay, so in this case, there were over 5,000 subjects per treatment group for over 20,000 total. So this large number of subjects helps to ensure that the difference in heart attacks was due to the aspirin and not chance variation in the random assignment. Okay, so it's not just saying, oh, we got one group that was all healthy people and they just happen to be the one that are taking the aspirin and they therefore have a reduced amount of heart attacks. Chance variation means that in that group there was people that were healthy, unhealthy, fit, unfit, well-balanced diet, not well-balanced diet. Okay, so who does this study apply to? So now we did this study. Be careful when you're doing an experiment what population it applies to. It only applies to male physicians like the ones in the study. So applying the results to anyone else won't be justified because they weren't part of our experiment. So it only applies to male physicians. Okay, so remember our slide on completely randomized design. So how do we make a diagram to represent a completely randomized experiment? So let's just take a look at how we are going to create that diagram. So let's use our 50 SAT students and and create a completely randomized design for the online course versus the course that's taken in the classroom. All right, so with our 50 SAT students, when you create your diagram, you always want to say, how many students did you start with? Okay, so who are the people in your experiment? Because remember that the results only apply to people like that in your experiment. So you want to state who and how many you started with. So we started with 50 volunteer students. Then, in order to make sure that we have to reduce variability in our experiment, we want to state when we're going to randomly assign. Remember that random assignment occurs before the treatment is given. So after we have our 50 volunteer students, we're going to then randomly assign them to our two groups, the online campus or the curriculum in the classroom. Then we want to make sure we state how many are in each group and what specifically is the treatment. So there were 25 students in the online group and 25 students in the classroom group. Now, when you are giving the treatments, you want to make sure there are equal number of participants within each group. What exactly are we going to measure? All right, you want to be specific here. We're comparing SAT scores. Don't just write the word compare, but because remember, somebody needs to look at this and be able to say, okay, what does their completely randomized design look like? What am I comparing at the ending? Specifically, I'm comparing SAT scores. Okay, there's one other thing that's important. You must include how the random assignment will take place. If not, you will not earn full credit. So let's just take a minute and see what that looks like. Okay, so now that you have your experiment outlined, you must include how the random assignment will take place. Can you remember how to do this from our previous slides? Okay, so here is one method. This is your hat method. This is very similar to sampling, but this is for your experiment. So key, first we're putting all 50 names of the students on identical pieces of paper. That's key. Put their names in a hat and shake it up. Shaking it up is also key. Pull out the first 20 names out of the hat. They will be in the online group. You have to state where the first 25 people are going. Don't just state pull 25 names out of the hat and then the other 25 will go to the other group. Specifically state what group they're going to. The remaining students will be in the traditional classroom. So we said where the first 25 will be and the second 25 will be. Okay, could we do this with the toss of a coin? So could I toss a coin and say if you get heads, you go to the online campus, and if you get tails, you go to the traditional classroom? Does that make sense? Well, no, it doesn't really make sense, because if we had each student come up with heads was online and tails was the classroom, due to random chance, every single person could end up in the online course, or you could have 40 people in the online course and only 10 in the classroom. So there's no way to guarantee that each group will have the same size. And if you remember, you want each treatment group to have exactly the same size. So we need to be careful with how we can use our random assignment. Okay, so what I would like you to do is take a minute, read this question, and then I would like you to design a completely randomized design for your experiment, and then write a few sentences on how you're going to implement your design. So if you need to, take a second, pause it, draw your completely randomized design, and then on the next slide, we'll take a look at the answer. Okay, so hopefully you pause the recording and we're able to create your completely randomized design. So let's see how you did. All right, so number one, always start with how many did we have? We had 60 children. With those 60 children, when are we going to randomly assign? And you can abbreviate random assignment as RA if that's easier. So with those 60 children, we're going to randomly assign them to the 3 tasks or TV programs that were our treatments. Okay, so each of these three groups have to be the same size. So we have 20 children in the fast pace, 20 children in the slow pace, and 20 children drawing. Notice how many are in each group and what treatment are they getting. Then at the end, you want to take a look at what are we comparing. Don't just write the word compare. Specifically, what are we comparing with our children? Mental ability and impulse control. If you want to think of random assignment as, hey, there's something else I have to add, make sure that you include that at the bottom. So we're using 60 equally sized slips of paper or identical pieces of paper. 20 of the slips are going to be 1, 20 are 2, and 20 are 3. We're mixing the numbers in a hat and having each child draw a number without looking. The number that the child chooses will be the group that she is assigned. At the end of the study, compare the mental ability and impulse control for the three treatment groups. Okay, so you could also then say slip 1 will be fast-paced, slip 2 will be slow-paced, and slip 3 is the children that are drawing. Okay, so here's another example. All right, so go ahead, take a minute and read this about music students. The first thing you're going to do is outline a completely randomized design for the experiment, so following the same model that we've looked at. Then I want you to make sure you describe how you will carry out the random assignment. Make sure that if you handed this to your classmate, they'd be able to implement your procedure. And then what is the purpose of the control group in this experiment? So remember, your experiment always needs to have some sort of control group. Okay, in the previous case, that control group could have been the students that were drawing because they weren't watching TV. So go ahead, take a minute, pause it, and try it, and then take a look at the answer. Okay, so we have, once again, we have our 29 students. Where are we going to randomly assign them? To small group, and then they're going to evaluate their study alone. And then the comparison over here, specifically here, it's going to be the accuracy of final performance evaluations. Now, if you notice here, 15 and 14, those numbers are different. In an ideal situation, you really do want to have these two groups to be the same size. Okay, make sure you explain the random assignment. All right, here's where that happens down here. Use 29 equally sized slips of paper, label 15 of them small group, 14 of them alone, shuffle the papers, hand them out at random to the 29 students to assign them a treatment. You could also do the hat method, that's also totally fine. Okay, so here's in Word, this is a paragraph form of our experimental design diagram. So we'll randomly assign the 29 students to the two treatments, evaluating the performance in small groups or the performance alone. The response variable will be the accuracy of their final performance evaluations. Both of these two methods are correct. I just think the diagram is easier to explain, and it's much easier for someone to look at and understand exactly how you're going to have your experimental design. So what was the purpose of the control group? All right, the purpose of the control group is to provide a baseline for comparison. Without a group to compare to, it's impossible to determine if the small group treatment is more effective. So comparison helps to give us cause and effect. So was the small group more effective? If we don't have anything to compare it to, we have no idea. Okay. So in the real world experiments, things can go wrong. The way that a randomized experiment works is that it depends on our ability to treat all the subjects in the same way every single time except for the actual treatments being compared. So basically with your randomized design, when you have your subjects in your experiment, you need to treat them all exactly the same. Give them the pills the same way, make sure they take the same amount of drink of water. They have no idea whether or not they're getting the placebo drug or the aspirin drug. Okay, for example, good experiments require careful attention to detail to make sure that all subjects are treated exactly the same. So if we were in the music classroom and we were dealing with the small groups versus the individual, you'd want to make sure all of the small groups were doing exactly the same thing. All of the people that were evaluating themselves individually were also doing that exactly the same. So we want to treat the subjects as identically as possible throughout the experiment. Okay, so what happens when you do get the placebo drug? Well, sometimes it looks like the placebo drug works. So people oftentimes know they're in the experiment. So a response to a dummy treatment is called the placebo effect. So the strength of the placebo effect is a strong argument for randomized comparative experiments. So the placebo effect is in the sense that, let's just say that we had our four groups with our male physician experiment. One of those groups was a placebo group. They did not get the aspirin or the beta carotene. Well, maybe they did have less heart attacks. That can be called the placebo effect. Therefore, because they think they were taking aspirin, maybe they were eating a healthier diet. Maybe they started exercising more. So they thought it was actually the drug that was making them better. So the placebo effect can be strong in some instances, so we want to make sure that we have a randomized comparative experiment so we have something to compare that placebo group to. Okay, so why would we use the placebo? When we're designing an experiment, you want all the subjects to be treated equally. So if you're giving pills in a medical experiment, half the group takes the pills and the half doesn't, know that they're not being treated equally. Remember getting a boo-boo as a child and having your parent kiss it to make it feel better? It wasn't actually an active treatment. It was sort of like a placebo. So this is just an interesting, that's why we use the little video about the placebo effect and depression. All right, so if you could just take a minute, take a look at that video. It's 60 minutes aired a segment about the placebo effect and depression. It's actually pretty interesting. So if you have a minute, go ahead and look at it. So what happens if you're the doctor administering the experiment? Are you going to expect less from your patients that are receiving a placebo? Are you going to interact differently with your patients that are receiving the placebo versus not? How can this be avoided? So how can we avoid knowing who's getting the placebo and who's not? Whenever possible, experiments with human subjects should be double-blind. Well, what does it mean to be double-blind? In a double-blind experiment, neither the subjects nor those who interact with them and measure their response know which treatment a subject received. Okay, so it's like going in a room and a doctor was handed four containers of pills, of various groups of pills. So he knew in container 1, this first group was going to get container 1. This second group would get container 2. This third group would get container 3. And the fourth group would get container 4. But he has no idea what drug is actually in each of those containers. And when he measures the response or the fact whether or not they had a heart attack, he doesn't know whether they took the placebo drug or the actual drug. Okay, so let's just think back to our caffeine experiment. So we were either taking caffeine soda or non-caffeine soda. How can this be double-blind? So remember, double-blind, the people getting the treatment and the people administering the treatment, the people don't know which treatment that they're getting, and the people administering don't know which treatment they're giving. The colors have to look and taste exactly the same. The people measuring the pulse and interacting with the subject should be unaware of who is getting which treatment. The subjects can measure their own pulse. This makes it blind because they don't know which drink they got. So they don't know which drink they got. They're measuring their pulse, and the people giving them the drink, they don't know who got what. Okay, then you might think for yourself, wait a second, how's this actually going to work? Someone had to know what drink they received, so is that really being double blind? It is a double blind as long as the person who knows who's getting which treatment does not interact with the subjects or taking their pulse, then it's still double blind. So it's like someone sitting behind the glass and, it looks like it's a mirror and they're looking in. They're looking at the experimenters and they're looking at the subjects, but they're not actually measuring the response variable. They're sort of looking in. They know who's getting what, but they have no interaction with the experimenters or the subjects. Okay, oftentimes what happens is people know they're part of an experiment, so double blind can be a little bit tricky. So oftentimes we deal with single blind experiments. So what if we're comparing two different exercise regimens to decrease marathon time? Well, the people that are getting the different exercise regimens are going to know which treatment or regimen they're receiving. So this is called single blind. So the people getting the treatment know which treatment that they're getting, but the people measuring the response variable or the marathon time have no idea who did what exercise regimen. So with a single blind experiment, the individual interacting with the subjects and measuring the response won't know who got which treatment. So at race time, they'll compare the results of the marathon without actually knowing who got what training schedule. Okay, so this is just a quick checking in. Did you understand the last couple of slides? So go ahead, take a minute and read this scenario and then answer the 3 questions. Okay, and then on the next slide we'll go over the answer. So if you need to pause the recording, I'll wait a few seconds for you to read it. So hopefully you're thinking in experimental language. So did they have a placebo? Why would it be important? Was the experiment double blind? Why would that be important? And based on your answers to questions 1 and 2, I want you to describe an improved design for your experiment. See how you did. Okay, number 1, there was no placebo effect here. The mothers who saw their unborn child could possibly have been encouraged to eat a better diet, resulting in healthier babies. So if there was a placebo effect, then they both would have gotten an ultrasound, okay? Or one would have been like a fake ultrasound and somebody wasn't actually looking at their baby on the monitor. All right, this was not double blind. It was most likely single blind. The people weighing the babies at birth may not have known whether or not their mother had an ultrasound, okay, but the mothers knew. So the experimenters did not, but the subjects did. This might have affected the outcome because the mothers knew whether they had received the treatment or not. So what they could have done is they could make it double blind. Treat all mothers as if they were having an ultrasound. However, for some of the mothers, the ultrasound would not actually be turned on. So in order to prevent the mothers from knowing whether or not the screen was turned on, they wouldn't actually be able to look at it. So the screen with the baby on it would be turned away from the mothers. So then the mothers wouldn't know whether or not they actually got the ultrasound, and then the doctors delivering the babies also would not, so that would be a double-blind experiment. So the person that actually did the ultrasound would know, but they're not interacting with the response variable. Okay, so I just thought this was kind of funny. So they often say laughter is the best medicine. So laughter is kind of like a placebo. Get a little humor in there every once in a while. Okay, so why do we need well-designed experiments? Well, the whole purpose of having experiments is so that we can perform inference for our experiments. So in an experiment, researchers usually hope to see a difference in the response so large that it's unlikely just to have happened by chance variation alone, right? So that just means if by chance, this group happens to be all the healthy people and they got the drug, they had a least amount of heart attacks. We want every group to be varied so that it didn't happen just by chance alone, but it was actually a response to the treatment. So we can use the laws of probability, which describe chance behavior, to learn whether or not the treatment effects are larger than we would expect to see if only chance were operating. Okay, so if we decide that it didn't happen just by chance alone and that the treatment actually caused a change in the response variable, we say this is statistically significant. So you're going to be using this throughout the rest of the year, so get used to this word statistically significant. This means that it didn't happen by chance alone. There was a reason that people's pulses were higher or babies were born at a healthier weight. Okay, so the official definition is an observed effect so large that it would rarely occur by chance is called statistically significant. So keep this in mind. So a statistically significant association in data from a well-designed experiment does not necessarily imply causation. Remember that an observational study is not an experiment. Therefore, with an observational study, you can never have causation. However, with a well-designed experiment, you can. That's why we want to have a well-designed experiment to see if our results were statistically significant. Okay, so let's just take a minute and think back to the caffeine experiment. How will we know if it's statistically significant? So basically we're asking the question, is there convincing evidence that caffeine actually increased the pulse rate? In other words, is the difference in mean pulse rate statistically significant? Well, how would we do this? We would repeat this experiment many, many times, and we would make a dot plot for the difference in the mean pulse rates. So if the mean pulse rates increased by 4, how often did we get this difference? If we got it often, then it might not be statistically significant, because if we're getting it often, that means we got it from the people that had the caffeine and the people that did not. So how can we make our experiments even better? There's a method called blocking. So what blocking does is, with a completely randomized design, those are the simplest statistical designs for experiments. But just with sampling, there are times when the simplest method doesn't necessarily yield the best results. So how can we make our experimental design even better? So what is a block? A block is a group of experimental units that are known before the experiment happens. Okay, they're similar in some way that is expected to affect the response of the treatments. So in a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. So basically all a block is if we were taking a look at, let's think back to the aspirin, and we think that there is, let's just say we have male and female doctors. Let's just say that when we look at the response, we're not sure whether gender or the drug helped reduce heart attacks. We would block them by gender. So what that means is they are similar, male versus female, and then within each block, all of the males would get 4 treatments and all of the females would get 4 treatments. Okay, so you block, and then within each block, they each get all of the treatments. Okay, we form blocks based on the most important unavoidable sources of variability. So think about the lurking variables that are going to affect your response variable the most. That's what you want to block by. Randomization will then average out the effects of the remaining lurking variables and allow us to have an unbiased comparison of the treatments. Okay, so if we block by male versus female, then the remaining lurking variables, such as maybe diet and exercise, are going to sort of be evenly distributed between those 4 groups in the male and the female. Okay, so the goal is to control what you can, block what you can't control, and randomize to create comparative groups that have less variability. Okay, so blocking. When you decide to block, you must be able to explain why you chose the method that you did to block. So for example, think about the caffeine experiment again. How could that be improved by blocking? Well, men and women have very different resting pulse rates. Blocking by gender helps to eliminate gender as the confounding variable. So you would want to state we blocked by gender because they have different pulse rates. Okay, that would explain why you chose that to block. We're trying to control for gender. Okay, we can't control male versus female, so since we can't do that, let's put them each in separate groups. Okay. When we're blocking, the block should be very different, male versus female, two different genders. At the end of the experiment, we're always comparing the results of the entire experiment, not just the blocks. Okay, so you're going to block, and then you're going to compare the block with all of the 4 groups, and then all 8 groups would be compared total. You're not going to compare the blocks separately. At the end, you would have compared all 8 of the groups from the aspirin experiment. How do we know which variable to use to block? Or we're going to block by the variable that has the strongest association to the response variable. Well, probably if we're doing the experiment with the aspirin, probably hair color has absolutely nothing to do with heart attacks, so we're not going to block by heart attacks. Okay, we could have also blocked by age and by gender, so that could be, those are 2 things that we could control for. Creating blocks is one of the most important, unavoidable sources of variation amongst experimental units. Okay, so think of what's going to affect the response variable and then block by that first. Randomization will average out all of the other lurking variables. Okay, so what does a blocked experiment look like? It's actually going to look pretty similar. Okay, so let's take a look at our caffeine example. Once again, what did we start out with? We started out with 50 men and 50 women, and then we blocked, okay, we didn't randomly assign yet, we blocked men with 20 and women with 30. Now notice these 2 groups do not have to be the same, but the treatment should be the same. Then with the men, RA stands we randomly assign them either caffeine or caffeine-free Coke. We compared the pulse rates of caffeine versus no caffeine, and then we combine the results to compare the pulse rates of everyone. We did the same thing with the women. Now here's where we randomly assigned caffeine, no caffeine. We compared the pulse rates, but at the end we compared the results of all 4 groups. This is combining the results. We're not comparing the block. So we're not comparing the block of male versus female. We're comparing the results of everyone. Okay, notice that the blocks don't have to be the same size. We just talked about that. But the treatments do need to be the same size. Okay, so what are some common experimental and sampling mistakes? So here's some things to watch out for. I know that experiments and sampling sort of sometimes sound like they have the same vocabulary, but they're very different. Do not confuse stratified random sampling with a randomized block design. Okay, stratified random sampling has to do with sampling. Randomized block design has to do with blocks. So stratified random sampling, remember, is when we break groups into stratas and then sample from each strata. Randomized block design is going to be where we block and then experiment. So the language of sampling and experiments are completely different. Sampling happens first, then with the sample we create the experiment. Stratified random sampling is done when we're taking a sample from a population. Blocking is done when we're assigning units to a treatments in an experiment. So blocking, BE, blocking is experiments. It's like stratified random sampling is like an SRS that only has to do with sampling. Do not write stratified in your experimental design. You will lose credit for mixing up the language of sample surveys, experiments, and observational studies. So understand the vocabulary difference between them all. Okay, so let's just take a look at what is wrong with this statement. So read it and then think about it for a second, and then we'll go over it. So we used a randomized block design to select the sample for the survey. Okay, what's wrong with that? We did not use a randomized block design. We used a stratified sample to select a sample, a stratified sample to select my sample. The stratified sample is for sampling. Randomized block design is for an experiment. Okay, let's take a look at the second one. The experiment suffers from non-response since the subjects dropped out during the survey. Okay, the experiment doesn't suffer from anything, but the sample does. The sample suffers from non-response since the subjects dropped out during the survey. So just make sure you understand the language of sampling versus experiment. Okay, so here's a little bit of practice with blocking. Go ahead, take a second and read this, and then try letter A. Why would a randomized block design be better? And then create a randomized block design for this experiment. Make sure you include how you're going to carry out the random assignment. So go ahead, pause the recording, take a second, try this, and then check out the answer. I don't know, but that cheese popcorn sounds good. Okay, so go ahead, take a look at the answers. Go ahead, take a second, pause, read them, and then I'll just show you some of the key aspects that you'll need for your answers. Okay, so hopefully you've been able to take a second and read the answers. All right, so completely randomized design basically ignores the differences between the four types of popcorn. So the four types of popcorn could pop differently on the popcorn button versus the non-popcorn button. However, a randomized block design takes a look at each variety separately and allows us to account for the variability in the number of unpopped kernels created by the difference in varieties. So take a look at this example in letter B. Now, in letter B, if you wanted to draw a picture or draw a diagram, I actually think it's easier to do that. If not, you can also explain it, but just make sure that you include how you're going to randomly assign. So here it is in the paragraph explanation. So to perform the random assignment, place all 10 bags in a large grocery bag. Shake the bag, then randomly select 5 bags to be popped using the popcorn button. Notice how it states what part of the experiment they're going to be. The remaining 5 bags will be popped using the instructions on the bags. Okay, so then notice, repeat this process for the remaining 3 varieties. So we stated where each of the 5 bags were going. Popcorn button, instructions on the bag. So make sure you just include that. Okay, so another way, so first we blocked by similar characteristics. Another common type of randomized block design for comparing 2 treatments is a matched pairs design. So the idea is to create blocks by matching pairs of similar experimental units. All right, now I just want you to take a look at the word matched pairs design, okay? Matched means similar, pairs means 2, and design. Don't ever try to say something is a matched pairs design if they're not similar and there's more than two. It's a randomized blocked experiment in which each block consists of matching pair, so similar pairs two of similar experimental units. So chance, so this is sort of random assignment, is used to determine which unit in each pair gets the treatment. Sometimes a pair in a matched pair design consists of a single unit that receives both treatments. Since the order of the treatment can influence the response, chance is used or random assignment is used to determine which a treatment is applied first to each unit. Okay, and we'll go over what this means. So matched pairs basically means two things. We have two people that are similar, so two females, similar age, similar height, that are going to take aspirin versus placebo. They're a matched pair, compare their results, or it can be a single person, all right, in which that person, they are their sort of own match pair. They get both treatments. Okay, so 1 year, if it's you're your own match pair, 1 year you get the aspirin, and then the next year you get the placebo. But you don't know which year you got the placebo, which year you got the aspirin. And then we take a look at the number of heart attacks. Hopefully nobody's having a heart attack once in every year, though. Okay, so keywords. Think matched. Matched means similar, the same characteristics. Pairs means two. There are only two ways to do a matched pairs experiment. Okay, way one. We put two subjects together that have similar characteristics. They have to be the same. So for the caffeine example, they would have to be two of the same age, female, same fitness level, maybe same sort of diets. They are very similar. We'll randomly assign one the caffeine Coke and the other the caffeine-free Coke. Then we'll compare the pulse rates just between the two subjects. We cannot use more than two subjects or two treatments for a matched pairs. It's always two. Two subjects, two treatments. So how would you randomly assign who got the caffeine, who did not? This still must be included. So in this case, only in a matched case, pairs case, will the flipping of a coin work. You could say heads was caffeine, tails was caffeine free. Have the first subject flip the coin. If they get heads, they drink the caffeine, and the other subject will drink caffeine free. If they get tails, they drink caffeine free, and the other subject will drink caffeine. When you do the heads and tails, make sure you explain, flip the coin. Okay, once again, I'm going to keep saying this over. Think matched pairs, similar pairs, there's two of them. There's only two ways to do the matched pairs experiment. That was method one. Here's method two. The subject serves as the control. Therefore, the subject is given both treatments. Okay, so you can either have two people, two treatments, one person, two treatments. The order of the treatments can influence the response. We randomize the order of each experimental unit. So for the caffeine example, the subject can drink caffeine-free Coke one day, take their pulse, and then drink caffeine Coke the next day and take their pulse. Compare the pulse rate after both experiments. However, the randomization will take place, okay, on deciding which day that you get caffeine, which day you get caffeine-free. So here's an example. Put numbers 1 and 2 on identical pieces of paper, put in a hat, mix it up, have the subject pick a number. If they pick 1, they'll drink caffeine Coke on day 1, and then on caffeine-free Coke on day 2. If they pick 2, they'll drink caffeine-free Coke on day 1 and caffeine Coke on day 2. Okay, this could also be done with a coin toss because there are only 2 treatments. Okay, it can't be uneven with assigning the treatments. Okay, so let's take a look at our standing and sitting pulse rates. Our standing pulse rates generally higher than sitting pulse rates. Take a look at how we can answer this question using a completely randomized design versus a matched pairs design. Okay, So take a minute, read the completely randomized. Okay, see if you have any questions on it. Okay, so completely randomized. The teacher is randomly assigning half the students to stand, the other half to sit. Okay, once they've been formed, the students should stand or sit as required, and they're going to measure their pulse rates for a minute. Everyone's recording their data, completely randomized. How does that look like in a matched pairs? So each person, okay, so this is where each person gets both treatments. There's only 2 treatments. Each will receive both treatments in a random order. So each student will sit for 1 minute, take their pulse, and each student will stand for 1 minute and measure their pulse. Okay, that will be assigned randomly. You would want to explain how that random assignment would occur, and then everyone will record their data. Okay, so let's just take a look at the Fathom dot plots from the completely randomized design and the matched pairs design described on the previous page. So what did the dot plots tell us about standing versus sitting pulse rates? Okay, so if we take a look, here's our standing pulse rates, here's our sitting pulse rates. To be honest, they look pretty similar, so I can't really say that there's a major difference between the two. However, okay, let's take a look at this, the matched pairs study. Note that the same scales were used, so we use the same scales 0 to 100 to help make a comparison regarding the variability of the response variable and the pulse rate. Take a look at this. This one was the actual pulse rate. This was the difference in pulse rates. This shows us the difference in pulse rates for each individual person. So there is a pretty big difference in pulse rates in standing versus sitting. Okay, so oftentimes a matched pair that reduces the variability between the people gives us a better idea on whether or not standing versus sitting has different pulse rates. Okay, so there was a difference almost every single time. Here it looks like the pulse rates are all pretty similar. Okay, notice the variability in the completely randomized design. So due to the variability, we can't make a conclusion that standing up causes an increase in pulse rate. However, using the matched pairs, we can make the conclusion that standing increases the pulse rate. Well, why? Due to blocking, we were able to reduce variability of the response variable, okay, because each person served as their control. Okay, so how could we do the same thing using 2 subjects? All right, so remember the other matched pairs, 2 subjects, similar characteristics. So have everyone in the class take their sitting pulse rate, arrange the students in order from the lowest pulse rate to the highest pulse rate, match the 2 lowest. Don't make the mistake of saying the highest and the lowest. That is not similar. 2 lowest pulse rates, the next 2 until the highest 2 have been matched. Randomly assign each student a treatment by having the students flip a coin. Okay, and then here's how the flipping of the coin would work. Okay, just make sure that you explain which is which. Heads, they're standing up or sitting down. The other student, tails, standing up or sitting down. How do you think the variability will compare to the blocked by subject matched pairs design? Okay. Most likely, it's going to have more variability in the pulse rates than the blocked by pairs, but less variability than the completely randomized design. Okay, so when we do use one person as the control, it reduces a lot of variability between the groups. Okay, that's probably the best way to establish cause and effect in an instance like this. Okay, that was a long section. So what did we learn? We took a look at the difference between observational studies and experiments. In an experiment, we have to impose 1 or more treatments on a group. The design of an experiment describes the choice of treatments and the manner in which the subjects are assigned to the treatments. The basic principles of experimental design are control, random assignment, and replication. Okay, many behavioral and medical experiments are double-blind. Okay, they help ensure the results. Okay, some experiments give a placebo or a fake treatment to control a group that helps confounding due to the placebo effect. So in addition to comparison, a second form of control is to form blocks. Okay, the randomization is carried out within each block, and matched pairs are a common form of blocking for comparing just two treatments. In some matched pairs design, each subject received both treatments in a random order.